Okay, so the recipe that we have just discussed of maximum entropy distribution is actually a recipe for learning about unknown distribution. So the idea is that, say, imagine that you have a random variable x, you don't know anything, then your starting probability distribution should be just the maximum entropy distribution, which is just a uniform distribution. Okay. Then imagine that now you make a measurement, and you know that the expected value of some function, let's call it f1 of x, you expect this to take value f1. Then this means that your distribution will be p1 of x, which is e to the lambda 1 times f1 of x divided by z lambda 1, which is the maximum entropy distribution that encodes this information and only this information, where the lambda 1 is given by the solution of the lambda 1 of log z equal to f1. Okay? Very good. So now you can continue this many times, and you can compute. You can think of you estimating a second function and find that this is equal to f2, or say that you estimate k of these functions, and so that you know that the expected value, or you expect that the expected value of fk is equal to fk. Okay, then at this point, so at each point you revise your theory, and here you have p2 of x, which will have an exponential form again, and then at the step pk of x, at step k you will have this state of knowledge, which is encoded in the distribution, which is e to the sum over I from 1 to k of lambda I times fi of x divided by z of lambda, where now lambda is the vector of all the parameters, and lambda I are given by the condition that the partial derivative of log z is equal to fi. Okay, very good. So now at every time, so you do this at every step, and then you can continue. So at every step, you can either check whether, say at every step, say for example, when you measure the expected value of fk plus 1, so there are two possible two possible cases. Either say the value of fk plus 1 is equal to the prediction of the earlier theory of pk, and then in this case there is no need to update your theory, and because essentially the value of lambda k plus 1 that you would measure from this would be essentially equal to 0. Otherwise, so if fk plus 1 is different, is significantly different from the expected value of fk of x, then you have to revise your theory, and lambda k plus 1 will be different from 0. Now, you can convince yourself that if you plot the entropy of the distribution P of k as a function of k, so you will start from k equal to 0 when you have essentially log of chi, and then at every step your entropy decreases, and it decreases because say as a function of lambda, as we have seen, the entropy is maximal at lambda equal to 0, and so whenever you have a situation where the value of lambda is not equal to 0, then your entropy will decrease. So if at step k you find that at k plus 1 you find this situation here, then the entropy will not decrease because the value of lambda is essentially equal to 0. But if you are instead in these other situations where the entropy of the value where the expected value of f this should be the expected value of f k plus 1 on the theory fk. So if you are in these other situations, then your entropy will decrease. Okay, so okay, very good. So now this is a general recipe, and the amount that you learn is precisely equal to the difference between the entropies of your theories. Okay, so now this is all okay if we deal with continuous discrete variables. So what about continuous variables? Then, well, for continuous variables there is a problem because as we have said, the differential entropy is not invariant under reparametrization. So it means that if I have a function f of x which is an increasing function, actually let me call it g, because I already used g of x, which is an strictly increasing function of x, then the random variable y, which is g of x, has in general an entropy which is different from h of x. So if I cannot state that the differential entropy measure my state of knowledge, because essentially it is clear that knowing x and knowing y, if you know x, of course you know y, and but the state of complete uncertainty, which would be the state of maximal h of x, would not correspond to the state of maximal uncertainty of y, okay, because they would correspond to different distributions. So, for example, let's imagine that we take, say, a Gaussian variable. So if we imagine, if we were to apply in a naive manner our argument above, we would say that if you have, if you know that the expected value of x is equal to mu, and the expected value of x squared is equal to, say, sigma squared plus mu squared, then our previous recipe would tell us that the optimal distribution would be the Gaussian, okay, 1 over square root 2 pi sigma e to the minus x minus mu squared over 2 sigma squared, because this is is an exponential distribution, and it has this exponential form, and it is consistent with these two observations that the mean is mu and the expected value is sigma squared. But now, say if I take the variable y, which is the square root of x, then for the variable y, this would correspond, these two conditions would correspond to the expected value of y being equal to of y squared being equal to mu, okay, so this would correspond to this, and this would correspond to the expected value of y fourth to be equal to sigma squared plus mu squared, and as a result you would get a different distribution, which is of the form e to the of y, if to the say lambda 1 times y squared plus lambda 2 times y fourth divided by some z of lambda. And you see that if you, these are not the same distribution, because if I change variable back from y to x, then I will not get exactly the same distribution because of the Jacobian. Okay, you can do this as an exercise. So we have a problem of, we cannot use the differential entropy in order to describe, to define a state of complete ignorance about a random variable x. So what James suggests is that we could use invariances, okay? We could use invariances and symmetries. So imagine, for example, the case where you have a random variable x defined in on the whole real axis, and imagine the problem of say, yes, estimating the probability distribution of x. Of course, the problem of finding what is the distribution of x is exactly equal to the problem of finding the distribution of x prime, which is say x minus mu. This is exactly the same problem which is just translated by a factor of mu. So whatever distribution I have for x, this should be equal to the distribution that I have for x plus mu. And this so what this implies is that the distribution that encodes my total ignorance about x, that I call P0 of x, should be a constant. Okay, so this is actually not a nice distribution, because if I take the integral from minus infinity to infinity in the x of such a distribution, then I get infinity, so this is not normalizable distribution. But this distribution, which is so this is why this distribution P0 is called an improper prior. Prior because it encodes prior knowledge, and improper because it is not normalized. But say if we take this distribution as our distribution, then you see that everything works fine, because essentially because say for this problem we would have for this problem here we would start from P0 of x, then if we measure that the expected value of x is equal to mu, and the expected value of x squared is equal to sigma squared plus mu squared, then the P1 subject to these two additional information would essentially be what I get from the maximum entropy recipe, and it would be just be the Gaussian, no? And this is because when I do this calculation, so I should have in general I should have e to the minus, I should have say P0 of x times e to the lambda whatever function I'm measuring of x, divided by the sum, well, the integral over x, the integral over x of P0 of x divided by e to the lambda f of x, say x prime. Now the trick I could use is to say, okay, so let's first assume that x is bounded between minus some big number lambda and lambda. So this integral would be finite. But then if this is a constant, if P0 of x is a constant, then it would just cancel from above and below. And so all I need is that then this integral here be finite, converts to a certain z of lambda as this big lambda, this capital lambda, this cutoff capital lambda goes to infinity. Okay. So in principle, there is a way to apply this idea of maximum entropy inference also if the variables are continuous, and by exploiting symmetries. Okay, so for example, another example of this is that if you know that your random variable is positive, so if you know that x must be positive, then essentially the problem of estimating x or the problem of estimating a times x, which is x prime, is essentially the same. So, or if you want, if you are in this problem, then you can revert to the previous problem by using the variable, say, y, which is log of x. So this would be defined on the whole real axis. And so you know that the non-informative prior that is consistent with a state of ignorance about y is the uniform one, is this improper prior. So this means that the improper prior, so the prior that is consistent with the state of ignorance about x should be of the form of P0 of x, which is a constant times 1 over x. And indeed you can check that this is with this prior, with the choice of this prior, these two problems will consist the PDF that encores the state of maximal ignorance about x and x prime will always be given by P0 of x. Of course, this also is an improper prior, because if I integrate from 0 to infinity in dx P0 of x, this diverges both at infinity and at minus infinity. But essentially, I can I can again use it as I did before by, say, for example, first assuming that x should be between, say, 1 over epsilon, between epsilon and 1 over epsilon. And then doing all my calculation, then letting epsilon go to 0. Okay. Okay. So then with these ideas, when we can exploit some symmetry, we can use this maximum entropy principle also for continuous variables. However, there is a problem, okay? So let us imagine that, yes, we have learned that, say, that the expected value of x is equal to mu, and the expected value of, say, x minus mu squared is equal to sigma squared. Then we conclude that our state of knowledge is consistent with a distribution which is the maximum entropy distribution consistent with these two observations, which is the Gaussian. Okay, so now let's imagine that we measure another quantity S, which is, let's say, the expected value of x minus mu cube. Okay, so what should we expect? So our expectation, we should expect that the expected value on this, say, let's call it P1, on the distribution P1 of S of x, that this should be equal to 0. Okay, so imagine that if instead we know that this is different from 0, then we should revise our probability distribution, say that P of x is equal to, say, P1 of x times e to the lambda times x minus mu cube divided by a normalization constant. Okay. So, however, the problem now is that if you compute the normalization constant, then this is an integral or that is essentially e to the lambda x minus mu cube times this P1 of x, and this is infinite. So there is no way in which you can make this integral finite if for any lambda which is not equal to 0, because this term here diverges faster than it dominates x to the minus mu squared in the distribution. Okay, so essentially there is no way in which I can use this maximum entropy inference in this particular case. So what is going on? So in order to understand what is going on, then one can think of a modified distribution P2 of x, which is made in this way. So let's assume that this is, so with probability 1 minus epsilon, this is the original distribution P1 of x. This is just the Gaussian, okay? But then with probability epsilon, this is just a delta function in a very large number, lambda, okay? And let's say that epsilon, I want to study this distribution for epsilon very, very small, okay? Now, if we ask what is the expected value of x over this distribution, well, this is 1 minus epsilon times the expected value over the distribution 1 of x plus epsilon times lambda, because this is the PDF of a constant which is equal to lambda. Okay, so this is essentially 1 minus epsilon times mu plus epsilon times lambda. So okay, so this is the first condition. So what is the second condition? Second condition is that we have to look at what is the expected value under this modified distribution of say x minus mu squared. So again, this is 1 minus epsilon times the expected value on the original distribution. This is just sigma squared. And then with the probability epsilon, this is equal to lambda minus mu squared. Okay, so very good. So now let us compute also what is the expected value on this modified distribution of x minus mu cube, and this is say with probability 1 minus epsilon it is 0, because this is the value you get from the Gaussian, and with probability epsilon it is lambda minus mu cube. Okay, now essentially what I want is that what I can do is that I can take a limit epsilon goes to 0, and I can require that lambda as a function of epsilon be such that when epsilon goes to 0, here I get mu, here I get sigma squared, and here I get exactly s. Okay, and if you check, I can do this if I take lambda of epsilon, which is equal to mu plus s divided by epsilon to the 1/3. Because if I do this, then I get exactly that as epsilon goes to 0, I can satisfy all these three equations. Okay, so what does this mean? Well, this means that this is that this modified distribution here, this p tilde of 2, is exactly like so this is if this were my original Gaussian, this is the P1. The distribution this P2 tilde is exactly the same distribution, but with a peak at lambda. Okay, and when epsilon goes to 0, this peak goes to plus infinity, and it gets smaller. Okay, so in the limit as epsilon goes to 0, this distribution becomes exactly equal to P1. Okay, so what does this mean? Well, it means that essentially when and you can also ask how much do you learn in this measurement. Well, you can see that the entropy of the new distribution P tilde 2 is essentially converges to the entropy of the old distribution P1. So this measurement, what this tells you is that, and this is clearly a distribution of maximal entropy. Okay, so what this tells you is that you have learned nothing by this particular measurement here. Okay, so to explain things differently, so you see that if you look at to put things in relation to other things that we have seen, you can see that the variable y, which is x minus mu cube, as a distribution. So if p of x, p1 of x is equal to the Gaussian, if this is equal to the Gaussian, then the distribution of this distribution of y is goes as e to the minus y to the 2/3. Okay, so it is times a constant, okay, which is this one. And so this distribution is a distribution that decays when y goes to infinity, slower than an exponential. So what we have seen is that if you have a distribution that decays slower than an exponential, then large deviations happen in a very special way, because essentially they happen by they concentrate. So one of the variable is much larger than the other, and this is exactly equivalent to this to what is happening here. Okay, so this distribution is a distribution that has all its mass in the whole distribution, but a very infinitesimal mass very, very far away in a very large point. So overall, this means that if you have a given theory P of k of x, and then you want to update this theory and learn something more about the random variable x. So you can measure the functions, the measurement that you can do, the f, how you should choose the fk plus 1, is must be such that the distribution, the PDF of fk plus 1 should have thin tails, because otherwise you will not learn anything. Okay, whatever your result is, or there is no way in which you can update your current state of knowledge to a new state of knowledge. Okay, so this puts some limits of what are the things that we can measure, or we should do experiment with. What are the theories? What are the objects? What are the learnable quantities, and what are the unlearnable quantities? In particular, the learnable quantities are only those which have a probability distribution which has thin tails. Okay, so this is interesting because it suggests that if your random variable x has a distribution p of x, which is e to the minus some e to the beta times some u of x, and as we have seen in the problem of where we were considering these very complex systems, and this variable u of x as a fat tail distribution, then there is no series of experiment by which you can learn this this function u of x. So these systems systems where the function u of x has fat tails as a fat tail distribution, they are unlearnable. Okay, you cannot learn these systems by a sequence of experiments.